Okay, as we talk about quadratics and eventually higher degree functions, we need to kind of slow down and talk about a concept called an imaginary number. An imaginary number is represented by I, and these have to do with the square root of -1. So for some time when you had a negative under a square root, you just stop and say no solution or this doesn't exist. But then along the way, imaginary numbers were developed, so you could still use these numbers that involve square roots of negatives that kind of don't really exist. You can't square anything and get a negative, but we can still kind of play along and just call it an I and still use them in some applications. So important thing to know is that I is the square root of -1, which means I squared is -1. I to the third, two of those i's make a -1, and then the other I is just left over and becomes -I. I to the fourth is to take two i's to make a -1, the other two i's make a -1, multiply those together and you get +1. And then the pattern repeats. I to the fifth is the same as I to the first, because four of the i's become a 1, and then that fifth I is just hanging on. So that just repeats itself. The sixth would be -1, the seventh would be -I, the eighth would be 1, and so on. Every four i's essentially just disappear. So what this allows us to do is simplify square roots that have negatives underneath. To remind you how to simplify something like the square root of 20, 20 is 4 times 5. So any perfect square can come outside the radical and its square root is taken. The 5 is stuck inside. All we will do is, if we have a negative sign underneath, is add an I to the outside. So long story short, an I on the inside, a negative on the inside of a radical is the same as an I on the outside. And if that number happens to be a perfect square, 3I is the square root of -9. So there's just some intro info about what I is and what imaginary numbers are. Okay, here's a secret that your math teacher might have never told you before. All of the numbers that you have ever used are called complex numbers. A complex number officially has a real part and an imaginary part. And I'll just do an example. 5 plus 3i. This is a complex number. Most of the numbers that you have worked with in the past have an imaginary part of 0. So technically they were complex, you just didn't consider the imaginary part. You just dealt with the real part. Okay, but a complex number is all numbers. The number 22 just happens to be 22 plus 0i, but we're going to start letting that imaginary part have some value in certain applications dealing with parabolas and other functions. The first thing we need to be able to do with complex numbers is add, subtract, multiply, and divide them. Adding is pretty simple. We're going to add them just like we would add x's and y's. We're just going to combine like terms. The 2 and the -5 are like terms, so 2 plus -5 is -3. And the 3i and the 7i are like terms for a total of 10i. I just acts like a variable in that case, just like an x or a y. We're just going to add like terms. So this is how you add two complex numbers. Subtracting two complex numbers, basically the same idea. I would encourage you to subtract these, pause for a moment, subtract them, and then come back and make sure you got it right. So remember, this negative sign is going to distribute to both parts, just like it would if you were subtracting polynomials. So we have -7 plus 1 is -6. We have -4i and then -6i after the negative distributes for a -10i total. So adding and subtracting, probably what you would guess, no big deal thus far. Okay, so let's multiply a couple of complex numbers. When we multiply this, we're going to FOIL. If you've used the memory trick FOIL, we're going to double distribute both parts to both parts. And we're going to have 4 terms and then simplify what we can. 2 times -4 is -8. 2 times 3i is 6i. Still just basically treating it kind of like a variable. -5i times -4 is plus 20i. 2 negatives make a positive. And then -5i times 3i is -15i squared. Now here's where something will be slightly different. The negative 8's going to stay the same. The 6i plus 20i make 26i, just like terms. But in this last term, we have an I squared. And as we talked about when we defined what I is, since I is the square root of negative 1, I squared is a negative 1. So long story short, anytime you have an I squared in a term, you can get rid of the I squared and change the sign. So I'm going to get rid of I squared, and that negative 1 that comes from I squared is just going to change the sign of that term to plus 15. Negative 15i squared is exactly the same as plus 15. And so then I can combine that with a negative 8 to get 7 plus 26i. All right, answer as a complex number. Okay, so to divide two complex numbers, we're going to use a technique called rationalizing. You've probably rationalized expressions that had square roots in the denominator. So just as a side note, if you had 2 over the square root of 3, this is irrational. You can't divide by an irrational number, so we multiplied by the square root of 3 over itself. At some point you probably did that. We're doing something similar. It's not really going to be the same. It's not going to look exactly the same, but it will be the same goal, to get rid of the irrational expression on the bottom. I is an irrational, so we have to fix that problem. All right, so let's see, let me get rid of that over there. Okay. And, all right, so how are we going to get rid of 2 minus 4i in the denominator? That's the problem, that being in the denominator. We need to use what is called the complex conjugate. A conjugate of something is that same expression, but with a plus instead of a minus, or a minus instead of a plus. 2 plus 4i is the conjugate of 2 minus 4i. Okay? These two expressions, conjugates. Now, the reason we'll use a conjugate is because when we FOIL it out, the O and the I parts of FOIL, the inner and the outer, will be exactly the same but opposites, and they will cancel each other out. So I'm going to FOIL on top. These are in parentheses. It helps me remember I need to FOIL. So on top, I get 6, 3 times 2, plus 12i, minus 10i, minus 20i squared. Okay? And on the bottom, on the denominator, I get 4 plus 8i minus 8i minus 16i squared. This feature right here, this O and the I parts canceling out, that's why a conjugate is so helpful. And you will use this fact in many applications as you keep studying further. What we end up with is on top, this minus 20i squared is the same as plus 20, as we just talked about a minute ago. This minus 16i squared is the same as plus 16, because an I squared changes the sign of any term. So on top, I have a 26 plus 2i. Okay, I can have i's in the numerator, just like I can have square roots in the numerator, not a problem. On the bottom, I have 4 plus 16, which is 20. All right, the 8i and the negative 8i go away. That's the beauty of multiplying something by its conjugate. Okay, so I want to simplify this a little bit. 26, 2, and 20 all have a 2 in common. So I can call it 13 plus I over 10. Or to put it in a plus bi form to make it look like our other complex numbers, I could call it 13 tenths plus 1/10 I. Just kind of divide by 10 here and divide by 10 here. Either one of those would be okay, but this would be a good final answer. So that's how you divide imaginary numbers. Multiply top and bottom by the conjugate, not the opposite. This is not the opposite, not the negative of this, because the 2 stays positive. It's just the sign in the middle changes from minus to plus or plus to minus. Okay, so let's end with a couple quick applications. Why do we need to deal with complex numbers? Every quadratic function this graph is a parabola, it has to have two solutions. So if I set this quadratic expression equal to 0, there must be two things that make this quadratic function equal 0. Now typically those are the x-intercepts, but this parabola doesn't have x-intercepts. This is a parabola whose two solutions are imaginary numbers, or complex numbers that have imaginary parts. So let's find the two values that make this true. This is a squared function, meaning it has to have two solutions. I don't see them anywhere down here on the axis, so they must be imaginary, so let's find them. Still use the quadratic formula as always. Negative b is 3, plus or minus the square root, b squared is 9, minus 4 times 2 times 5, all over 2a, that's 4. 3 plus or minus 4 times 2 times 5, that's 40. This is 9 minus 40, or negative 31. 9 minus 40, negative 31. 4 on the bottom. And at this point, 31 is not going to simplify. So here are my two answers. Complex or imaginary solutions to quadratics always come in conjugate pairs. Make sure you write down this fact and remember it. When you do the quadratic formula to find the two zeros of this quadratic function, they're not real because they're not actually x-intercepts, but there has to be two things that make it 0. Here are the two, and they naturally just come in conjugate pairs. Now I could take the I out and write this as 3 plus or minus I times the square root of 31 over 4. That's a little more proper than the negative under the square root. But either way, there's always going to be this plus or minus, and they're always going to come in conjugate pairs. Which means if I tell you one of the two solutions, you automatically get the other of the two solutions. Now let's talk about that a little more. To back up this next example, the final example, we're going to do this as a little bit of background. If you want the quadratic that has zeros, 3 and negative 5, we're looking for ax squared plus bx plus c. The c is negative 15. That's 3 times negative 5. And the b, we want to add 3 and negative 5 and then take the opposite. 3 minus 5 is negative 2. The b is going to be positive 2. And this is going to be a 1x squared. This is how you do that quickly. This came from this fact. If a 0 is 3, then a factor was x minus 3. If a 0 was minus 5, then a factor was x plus 5. If I FOIL this out, I get x squared plus 2x minus 15. But we can shorten that process by multiplying these two numbers, and that goes here. Adding these two numbers and taking the opposite, that goes here. That applies for imaginaries also, so I want to do this as a quick example to introduce you to this next one. Okay, so our question is, write a quadratic equation with 0, 2 plus 3i. So let's just start with the fact that these things always come in conjugate pairs, so the other one is 2 minus 3i. And rather than doing x minus these and multiplying it all out, which you could do, it's a lengthy process, we're going to do the trick. If I add these two numbers, my answer is going to be in the form x squared plus something x plus something. If I add these two numbers together, what do I get? If I add them, I get 4 because the imaginary parts go away, and I get 4. The opposite of that is minus 4. So I could say minus 4 plus negative 4, either way. If I multiply these two things together, 2 plus 3i times 2 minus 3i, FOIL it out, I get 4 minus 6i plus 6i. There's the conjugates, o and I going away out of the FOIL. These two will be gone. Minus 9i squared. 9i squared is the same, minus 9i squared is the same as plus 9, and this becomes 4 plus 9, or 13. So, x squared minus 4x plus 13 is the quadratic that has 0, 2 plus 3i. Add them, take the opposite, multiply them, put it here, and there it is. Okay, so our main focus is working with imaginaries, but I wanted to go ahead and give you a couple of applications that have to do with quadratics. And so that just adds to the things we can tell about quadratics. That'll do it for this one.